if you don't understand the very mechanism this way, if you don't understand and tap into this, then you're only going through equations after equations, and beyond a point of view, you have a limitation. You can deal with 20, 30, 40, 50. You can't deal with 500. You can't deal with 200. Even 100 is too much. Even 50 is too much without logic. I've seen children starting in the beginning, things are going very rosy, nice, logical approach, physical chemistry is very nice. As soon as organic chemistry begins, they start panicking. And that's why children from all these so-called institutions, they come back to me, and I have to every time make some batches separate for them, because in their school some different speed is going on and they're stuck and facing difficulty in the same mechanism part and all that. So alkynes, yeah, we have already completed alkanes and alkenes. Now we are jumping on to alkynes. Correct. Some of the basic things are details are given about the alkynes. Correct. This is also an unsaturated compound. In fact, it has greater degree of unsaturation. Correct. Two, what do you say? Pi bonds are present, so 2 degree of unsaturation will be there. Correct. I want you to go through these basic things. I'm not discussing that. Read it. Correct. And that will be easy for you. Usually the structure of alkynes are 1 sigma bond, 2 pi bonds. The bond length is given here. Bond energy is given here. Correct. 1 triple bond is present. What is the hybridization? In hybridization, you only count sigma bonds. Correct. Correct. So hybridization is sp hybridized. All that is what is talked about here. Good. Good. Then what is the bond angle? All that is, 180 degree and all that. Fine. Go through this. These are basics. Same way, I hope you also remember the IUPAC nomenclature which we did in the past. Yes? You know how to name these alkynes. Good. I'm even skipping these also. You know how to do that. Like in this case, there is a triple bond. If you start from this side, 1, 2, 3. If you start from this side, 1, 2, 3, 4. Which side will you begin? Left, obviously. Good. So 1, 2, 3, you will have your triple bond. So 3-ine is written. Yes. After that 4, 5, 6, 7. So at 6th carbon and then the 2nd carbon, you have methyl and bromine respectively. So what should we do? Alphabetically we will write. Bromo, B comes first, methyl M comes later. So 6 bromo, 2 methyl, total 7 carbons. So hept, 3-ine. Good. This is how we can do naming. Even isomerization, we have taken it previously. So this also I'm kind of skipping. Here chain is being going from a straight chain to a iso chain. Yes, so I hope you can remember that also. Here also chain isomerism is happening. Here the location of the triple bond is changing, so position isomerism. Here the functional group itself is changing. From triple bond we are going to a cumulated diene. Yes or no? What do you call when the double bonds are close by? Cumulated diene. Correct. They are different functional groups but same molecular formula, so that is also functional group isomerism. Then alkynes are also, they also form ring and chain isomer with whom? Cycloalkene. Yes or no? Yes or no? Alkenes form with cycloalkane, alkynes form with cycloalkene. Remember that. Their molecular formula will be same but different. This is also called as ring chain isomerism. But since kind of functional group is also changing, so it is also called as functional group isomerism. Good? Good. Then another thing, cis trans isomerism is not possible in alkynes. Why? Obviously 180 degree bond angle. Yes or no? 180 degree bond angle, that means cis trans is not possible. Yes? Draw the geometrical isomers of hep2-ene 5-ine. Now here geometrical isomerism will not happen at the triple bond, rather it will happen at the ene. That means at the double bond. That is possible. So now one might say, sir, one question before only we discussed that cis and trans cannot happen in alkyne. But now we are seeing a cis and trans because cis and trans is only happening at the carbon-carbon double bond junction. Yes, not at here. Here it is not happening. Good. So that remains, the whole thing remains as an adjacent to a carbon, double bond carbon. Good. Fine. We, from the basic properties, now we move on to the general method of preparation. As I told you in the past already, we already saw this reaction where geminal dihalides, that means dihalides which are connected to the same carbon, can be converted into alkynes. We have already seen this. Yes or no? This process is called as dehydrohalogenation. You're removing hydrogen and the nearby halogen. Yes, you remove dehydrohalogenation, you do it, what you will get will be an alkyne. Is that clear? You remove these two fellows, in short I am telling you this, that will turn into a double bond. You remove these two fellows, that will turn into a double bond. Mechanism is not that simple, I am just telling you trick wise, shortcut trick. Yes or no? Correct. Mechanism is as it was happening in the usual elimination reaction. Yes, usual elimination reaction, it used to happen. Okay, fine. Let's jump on to this. So alcoholic KOH is being used and dehydrohalogenation will take place. So first HX is removed, so you will get something like this. This will be stabilized because of resonance, and then later on you use sodamide. What do you call this fellow? Sodium connected to amine is called as sodamide. Yes, yes. So this sodamide, you use it. These are the dehydrohalogenating agents. Alcoholic KOH is also that, and sodamide is also that. Yes. Apart from that, sometimes we can also use alcohol along with RONA. Yes, sodium alkoxide. Alcohol along with sodium alkoxide, that also can be used. Correct? Another HX will leave. What do you have at the end? Alkyne with you, with sodium halide, yes, and NH2 taking this H plus amine. Good. I hope it is clear what happened here. Good. Due to stability of vinyl halide by resonance, this is vinyl halide. Because of the stability of vinyl halide by resonance, there is partial double bond in which elimination does not take place by alcoholic KOH. And that's why we go for a stronger base. Who is that? Sodamide. Yes. I hope it is clear. Everybody understood? Basic strength, if you check, again, NH2 minus is stronger than even NH2 minus is stronger than even OR minus. Remember that. NH2 minus is even stronger than OR minus or RO minus. Good. Another thing, here the elimination doesn't happen on the same side, which is called a cis elimination or syn elimination. It happens on the opposite sides. That's why it is trans elimination. And I hope you remember the beta elimination situations. Remember, we used to have something like this, here some bromide ion connected and here some hydrogen connected. So beta elimination, this will be snatched away, then this will jump here, and then this will be snatched away. So that's how trans elimination is happening. Yes or no? This and this in a trans position is being eliminated. Good? Good? I hope you remember that from the GOC chapter. Yes? Fine. From geminal dihalide we have understood. Similarly, from vicinal dihalide where they are side by side, what will happen now? What will happen now? Exact same process. Exact same process. Exact same way of removal. You remove H plus from here. This will jump here. Correct? And this will be taken out. I hope it is clear. Good. And then next time do the other way. But only thing is, once you remove it, it becomes, resonance point of view, it becomes quite strong. So then you have to use a stronger base. Yes or no? Which will help in elimination. Ultimately, you get your alkyne. So elimination of the vicinal dihalide also gives alkadiene, either 1,2 or 1,3. Good. But the major product is always alkyne. Remember that. Example is right here in front of you. Here also you can get alkadienes, in fact cumulated diene, but major product will always be your alkyne. Yes or no? Yes or no? That means double bond here, the double bond can form here. Somebody took away H plus. This will jump here. This will be taken away. Yes or no? Yeah? Everybody understood? Similarly, if somebody takes away this, even this fellow can jump here rather than jumping here. So here also double bond, here also double bond. Chances of formation of alkadines, cumulated dienes. You understood? That's why they're even isomers of each other. Yes, because chances of forming is there. Okay. Non-terminal geminal dihalide. If you don't understand the very mechanism this way, na, if you don't understand and tap into this, then you're only going through equations after equations, and beyond a point of view you have a limitation. You can deal with 20, 30, 40, 50. You can't deal with 500. You can't deal with 200. Even 100 is too much. Even 50 is too much without logic. Yes or no? So these connections are important, and I hope when I'm explaining you are writing them down also. Otherwise, mechanisms make the whole organic chemistry very crazy. People are they are very much troubled. And you see the way these coaching institutes are designed. I've seen children starting in the beginning, things are going very rosy, nice, logical approach. Physical chemistry is very nice. As soon as organic chemistry begins, they start panicking, and that's why children from all these so-called institutions, they come back to me, and I have to every time make some batches separate for them, because in their school some different speed is going on, and they are stuck and facing difficulty in the same mechanism part and all that. For your batch we are still beginning, so I'm telling you guys, so if anybody is there, friend around or somebody who is also facing difficulty, talk to them, please. Ask them, this is high time they should come, otherwise they'll miss out. Okay, good. So non-terminal geminal dihalides, if we have, what are non-terminals? That means not on the end carbons, 1 degree carbons. Yes, they are on the middle somewhere, like here. Yes, non-terminal geminal dihalide. In this case, what will happen? This one the major product is alkyne formation here. Good. That means here and here, triple bond formation. Another is here or here. So obviously, with the middle carbon, it will be a major product, more stable, and with the terminal carbon, it will be the minor product. Oh, what did they do? Acha, acha, sorry. If you're using alcoholic KOH, which is a weaker, what do you call, eliminating agent, then what will it do? Then this case will happen. This will be the major product. But if you're still using a stronger fellow, then he will snatch this will be gone, and this terminal alkyne will form. Is this part clear? Yes. Non-terminal geminal dihalides gives 2 alkyne in the presence of alcoholic KOH, 1 alkyne in the presence of stronger sodamide, stronger base. Good. Fine. Keep that in mind. All that is because of the strength, basically. Understood, na? Because of the strength. Now this will jump and snatch away the H plus, then this fellow will jump the other side. That is how it happens. Correct? So in this case, usually what is happening is, let me do this to show you one thing. I'm not going back to again remind you how does beta elimination take place. I hope you remember that. So alcoholic KOH usually will strike from which side? It will strike from on this hydrogen, and it will take it away. When it takes it away, this will jump here, this will jump here. Understood? So double bond formation will happen. Correct? And then similarly in the next case, it will jump from here, snatch it away, this will jump here, this will leave. Good. So triple bond here in the middle. But when NaH2 has to attack, this is more bulkier, more stronger also, it will go for the terminal hydrogen. When it does the same thing to this terminal hydrogen, yes, this lone pair of the NaNH2 on this hydrogen, then what will happen? Terminal alkyne will form. I hope you understood. Good. Keep drawing these things, very important. Otherwise, you're going to miss the crux. Nice. Yes. Dehalogenation. Now let's jump on to the dehalogenation part. Okay. Dehalogenation of tetrahaloalkane. When you heat it, yes, when you have 1 2 4 1 1 1 2 2, that means there are tetrahaloalkanes. Then also all the halides dehalogenation will happen. Same way, triple bond formation, alkyne formation is possible. Only thing is you have to use a strong reducing agent. For that, zinc dust is being used. Good, fine. And zinc is what? Zinc is what? Divalent in nature. Bring one zinc here, bring another zinc here. It will tend to connect with X, forming ZnX2. Yes, this thing breaks. Got it? Draw it, draw it, draw it, draw it, draw it. This is the link. That's how you remember what will zinc does to a tetrahaloalkane. Good. Then comes coal-based electrolysis. This is, I think, fourth time we are seeing it. Yes or no? Once in GOC, then in alkane, then in alkene, now in alkyne. Exactly same procedure. Only thing is, this time we are doing coal-based electrolysis of not an uh, uh, alkane. We are doing it for alkene. Yes, yes. Acetylene formation. That means ethyne formation happens here. Correct. And we have a sodium in place of potassium. Even sodium can also be there. So sodium fumarate or malleate depends on how many carbons are present. Yes. If there was one hydrogen, correct, then in that case it will be fumarate, otherwise malleate, all that. So point is, this undergoes electrolysis, correct. CO2 leaves, this one fellow jumps here, this fellow, CO2 leaves, so we have alkyne formation and CO2 coming out, correct. Mechanism, I hope you guys know already, that it breaks down into ions first, and anions go to anode, cations go to cathode, correct. That's why the alkyl and the CO2 gas is formed at anode, correct. You have a free radical present here. Now that free radical shift will happen, CO2 will leave at the end, correct. This will jump here, this will jump here to form a triple bond. Here also CO2 leaves, so 2 moles of CO2 are gone. We have alkyne present. At cathode, it is simple, KOH and hydrogen gas, potassium hydroxide and hydrogen gas is formed, and that's how it is removed. Good. Okay. One very important question. pH of the solution, does it change when it comes to coal-based electrolysis? Yes. Why? The concentration of NaOH or PaOH or KOH solution is increased. So obviously what will happen to the pH? pH will also increase with time. Is that clear? You see KOH is being formed now. Whatever K plus was, cation was produced here, that cation will go to cathode. Yes. So once it goes to cathode, what it does? It gains electron there, forms potassium atom. That potassium atom combines with water, forming KOH. Nice. Any doubt? No doubt. Sangvi understood. Same thing happened other places also. Yeah. Okay. So concentration, pH of the solution is going to increase. Next, we can also prepare alkynes using Grignard reagent. Only thing is, this time we have to attack it on another alkyne. Then you can produce another alkyne. That means if you use it, let's say this alkyne is present and you're using another methyl magnesium bromide, what will happen? MgBr will go to one carbon and H plus will go to another carbon. Good. This is what will be your immediate product. Yes. After that, bring any alkyl iodide. Then this carbon will be eliminated by iodide. Iodide will get connected to magnesium, and you will have Rc triple bond H. That alkyl fellow will go and join in place of this, and MgBr will get connected to iodide. Nice. Correct. Change the number of carbons in the chain. Exact same thing will happen. Good. We have R dash and R both connected. Same way, we can also produce acetylene or ethine via some old industrial processes. One of that is the use of carbide, calcium carbide. We use the same thing even to produce what? Alkene. Do you remember? Yes, but this is a very old method. In laboratory also you can do this. Take calcium carbide, correct? Uh, React it with water, heat the water and react it with water. You will have alkyne formation along with calcium hydroxide being given off. So what happens? Ca2 plus and 2H plus, all the ions are broken down here. H plus goes and joins here, and Ca2 plus combines with hydroxide ion forming calcium hydroxide. Good. Another method is, which is an industrial method which requires high degree of temperature or sometimes electricity. Yes, correct. Using an electric arc, that temperature is reached, that is 1500 degrees Celsius, where we can directly use natural gas. So natural gas is a rich source of methane. Yes or no? So basically, when you use natural gas or sometimes directly methane gas, we can actually obtain again ethane. Yes, but let me tell you, these processes, whether it is using metal carbide or using natural gas or methane, we are only getting ethane or acetylene. Yes, not the other alkynes. I hope that part is clear. Good, good, good. That part is clear. Okay. Berthelot's process, again same thing. Take acetylene and pass it through an electric arc at 1200 degrees Celsius, also in the presence of hydrogen gas. Then you will get ethine. Haloform process. This time, what are we using? CHI3 or CHCl3, which is called as, this is this is iodoform, this is chloroform. So either of these can be used along with what? Along with silver powder. Some silver powder, so silver iodide will form, and rest CH will connect with each other as again acetylene or ethine. Again, partial oxidation also we can do. Partial oxidation or extreme form of oxidation is combustion, that also we can do. So here combustion is happening, producing what? 1500 at 1500 degrees Celsius, again producing ethine and water. Good, good. Just clear. Fine.